Right now, somewhere in space, there's a planet where it rains molten glass sideways at 4,500 miles per hour. In another world, diamonds literally fall from the sky like hailstones. And in one corner of our galaxy, there's a cloud of alcohol floating in space that could supply Earth with beer for the next trillion years. These aren't science fiction fantasies. They're documented scientific facts that sound absolutely impossible. For centuries, humans looked up at the night sky and imagined what might be out there. We dreamed of other worlds, alien civilizations, and cosmic wonders beyond our comprehension. But here's what makes the reality of space more disturbing than our wildest imagination. The universe is stranger, more violent, more beautiful, and more incomprehensibly weird than we ever dared to dream. Every week, astronomers discover something that completely breaks our understanding of what's possible. A star that shouldn't exist according to our physics. A planet orbiting its sun so closely that its year lasts just 16 hours. A galaxy that's somehow older than the universe itself. These discoveries don't just expand our knowledge, they shatter our assumptions about reality. Tonight, I'm sharing 100 space facts that will fundamentally change how you see the cosmos. Not abstract theories or mathematical equations, but concrete, mind-bending realities that exist right now in our universe. Facts so incredible that if someone told them to you at a party, you'd assume they were making it up. Yet, every single one has been verified by NASA, the European Space Agency, or peer-reviewed astronomical research. We'll journey from the familiar strangeness of our own solar system to the absolute chaos happening in distant galaxies. You'll discover that Neptune has winds that make Earth's hurricanes look like gentle breezes. That there are stars so dense that a teaspoon of their material would weigh 6 billion tons. That space itself is expanding so fast that galaxies are moving away from us faster than the speed of light. Something Einstein said was impossible. But these aren't just random cosmic trivia. Each fact reveals something profound about the nature of reality itself. They show us that the universe operates on scales and principles so far beyond human experience that they challenge our most basic assumptions about existence. When you learn that time moves differently on different planets, or that there are regions of space where physics as we know it simply breaks down, you start to realize that Earth isn't just rare. It's a miraculous oasis of normalcy in an ocean of cosmic insanity. Some of these facts will make you laugh. Others will keep you awake at night wondering how we can exist in such an impossible universe. A few might fundamentally change how you think about your place in the cosmos. All of them will remind you that reality is far stranger and more wonderful than fiction. Consider this. Right now, you're sitting on a planet that's spinning at 1,000 miles per hour, orbiting a nuclear reactor at 67,000 miles per hour, while that entire solar system rockets through the galaxy at 514,000 miles per hour. And somehow, your coffee isn't spilling. That's just the beginning of how weird space gets. From planets made of diamond to the sound of black holes singing, from the smell of space to the color of the universe itself. We're about to explore cosmic truths that will stretch your imagination to its absolute limits. These aren't distant abstractions. They're the reality of the universe we inhabit. If you're fascinated by the hidden weirdness of our cosmos, subscribe and hit the thumbs up button. And here's a question that'll make sense by the end. If you could smell space, would you expect it to smell like burnt metal, welding fumes, or barbecue? Comment below. I'll pin the most creative explanation. Throughout human history, the impossible has become routine. We've learned that the Earth moves, that atoms exist, that light has a speed limit. But each new discovery about space reveals that impossible is just another word for not yet understood. The universe doesn't care about our limitations. It operates according to its own bizarre rules. And those rules produce phenomena that would be rejected as too unrealistic in science fiction. Tonight, we're not just learning facts. We're expanding our definition of what's possible. We're preparing our minds for a universe that's simultaneously beautiful and terrifying, logical and completely insane. A universe where diamond rain is normal, where time is negotiable, and where the impossible happens every second of every day. Are you ready to discover just how strange your cosmic home really is? Let's begin this journey into the magnificent madness of space. Chapter 1: Cosmic Basics. Before we dive into the truly mind-bending facts about space, we need to establish just how weird normal cosmic conditions really are. The baseline reality of our universe is already so strange that it makes everything else seem almost reasonable by comparison. Let's start with something fundamental: silence. Space is completely, utterly silent. Not quiet, silent. Sound requires matter to travel through, and space is essentially nothing. When massive stars explode with the energy of billions of nuclear weapons, when black holes devour entire solar systems, when galaxies collide in slow-motion disasters spanning millions of years, it all happens in perfect, eternal silence. The most violent events in cosmic history have never made a sound. But here's where it gets weird. Space isn't actually empty. What we call the vacuum of space contains about 1 atom per cubic centimeter. That sounds like nothing until you realize that there are more empty cubic centimeters in the observable universe than there are grains of sand on every beach on Earth. All those empty regions add up to more matter than exists in all the stars combined. The universe is mostly made of stuff we can't see, floating in regions we think of as nothing. Temperature in space is equally bizarre. The baseline temperature of the universe is minus 454 degrees Fahrenheit, just barely above absolute zero. At this temperature, atoms practically stop moving. Yet step into direct sunlight in space, and temperatures can soar to 250 degrees Fahrenheit. Astronauts experience both extremes simultaneously. The side facing the sun burns, while the shaded side freezes. It's like standing in front of a campfire in Antarctica. Time itself behaves strangely in space. Einstein proved that time moves differently depending on your speed and gravitational environment. Astronauts on the International Space Station age slightly slower than people on Earth. After a 6-month mission, they return having aged about 0.01 seconds, less than they would have on the ground. It's a tiny difference, but it's real and measurable. Time isn't the constant we experience on Earth. It's negotiable. The scale of space defies human comprehension in ways that go beyond simple big numbers. Light, the fastest thing in the universe, takes 4.37 years to reach us from the nearest star. That star, Proxima Centauri, is considered our cosmic next-door neighbor. If Earth were a grain of sand, Proxima Centauri would be another grain of sand 4 miles away. The distance to the center of our galaxy would stretch from New York to Japan. And our galaxy is just one of 2 trillion galaxies in the observable universe. Gravity in space creates effects that seem to violate common sense. Astronauts don't float because there's no gravity. They're actually in constant free fall along with their spacecraft. The International Space Station is falling toward Earth right now, but it's moving so fast horizontally that it keeps missing the ground. This is what orbit really means: falling forever and never hitting anything. The speed of cosmic rotation is staggering. Earth spins at 1,040 miles per hour at the equator. It orbits the Sun at 67,000 miles per hour. Our entire solar system rockets through the galaxy at 514,000 miles per hour. The galaxy itself moves through space at 1.3 million miles per hour. Right now, as you sit reading this, you're moving through space faster than you've ever moved in your life, in multiple directions simultaneously, and you feel none of it. Space changes the human body in ways that reveal how perfectly adapted we are to Earth-specific conditions. Without gravity, astronauts' bones lose density, their muscles atrophy, their hearts weaken, and their blood pools incorrectly. Their spines lengthen, making them taller. Their faces puff up as fluids redistribute. These changes begin within hours and continue throughout their missions. We are literally built for this one specific planet's environment. The electromagnetic environment of space would kill unprotected humans in multiple ways. Solar radiation, cosmic rays, and particle storms constantly bombard everything beyond Earth's magnetic shield. This radiation isn't just dangerous, it's creative. It causes computer glitches, creates artificial auroras, and can literally alter the DNA of living organisms. Space actively rewrites the genetic code of anything exposed to it. Perhaps strangest of all is what space smells like. Astronauts report that space has a distinctive odor that clings to their spacesuits: hot metal, welding fumes, and burned steak. This smell comes from atomic oxygen, single oxygen atoms created when solar radiation breaks apart oxygen molecules. These lone atoms are desperately reactive and immediately bond with whatever they touch, creating the metallic scent of space. The darkness of space is absolute in a way we can't experience on Earth. Even the darkest night on our planet is illuminated by starlight, moonlight, or atmospheric glow. In space, if you're in shadow, you're in complete, perfect darkness. Astronauts describe it as a blackness so profound it seems solid, like looking into an infinitely deep hole in reality. Yet this same space that seems so hostile and strange is actually our home. We are not separate from space. We are space creatures living on a space rock, made from space dust, breathing space atoms, looking up at space neighbors. Everything about our existence, from the calcium in our bones to the iron in our blood, was forged in the nuclear hearts of dying stars and scattered across space by cosmic explosions. Understanding these cosmic basics changes everything that follows. Every weird fact we'll explore exists within this framework of impossible normalcy. Space doesn't just contain strange phenomena. Space itself is the strange phenomenon. We're about to discover just how strange it gets. Chapter 2: Planetary Madness. If you think Earth's weather is unpredictable, wait until you discover what passes for normal weather on other planets. The cosmic neighborhood is filled with worlds where the impossible is routine, where physics creates conditions that would be rejected as too extreme for science fiction. On HD 189733b, a planet 63 light-years from Earth, it rains molten glass horizontally at 4,500 miles per hour. The planet orbits so close to its star that temperatures reach 1,700 degrees Fahrenheit, hot enough to melt glass. High-altitude winds moving at speeds that would make Earth's jet streams look motionless carry these molten silicate droplets across the planet's surface like sideways bullets of liquid glass. The planet appears brilliant blue from space, not because of water, but because of this deadly glass precipitation scattering light. Neptune experiences winds that dwarf Earth's most powerful hurricanes. The fastest winds on our planet peak around 200 miles per hour. On Neptune, routine wind speeds hit 1,200 miles per hour, faster than the speed of sound on Earth. These supersonic winds circle the planet in massive storms larger than our entire planet. What makes this impossible is that Neptune receives only 1% of the sunlight that Earth gets, providing almost no energy to drive such violent weather. Scientists still don't understand how these winds achieve such incredible speeds with so little energy input. Venus proves that greenhouse effects can create hell worlds. Its atmosphere is 96% carbon dioxide, creating a runaway greenhouse effect that makes the planet hotter than Mercury despite being farther from the Sun. Surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is 90 times greater than Earth's, equivalent being a kilometer underwater. It rains sulfuric acid, and the atmosphere is so thick with acid clouds that the surface gets less sunlight than Earth receives during a heavy thunderstorm. On Jupiter's moon Europa, geysers of water shoot 125 miles into space through cracks in the ice. This moon, covered entirely by a frozen ocean, has more liquid water than all of Earth's oceans combined, hidden beneath miles of ice. The water remains liquid due to tidal heating from Jupiter's immense gravity, which flexes and heats Europa's interior like kneading dough. These geysers represent water that has been liquid for billions of years, potentially harboring life in an underground ocean that has never seen sunlight. Saturn's moon Titan has lakes and rivers, but they're filled with liquid methane and ethane instead of water. This moon has weather cycles, seasons, and precipitation, all involving hydrocarbons. Methane rain falls from methane clouds, creating methane rivers that flow into methane lakes. The landscape looks eerily Earth-like in photos, complete with coastlines, islands, and deltas. But this familiar terrain exists at -290 degrees Fahrenheit, where methane behaves like water does on Earth. Mercury experiences temperature swings that would shatter most materials. During its 88-day year, the day side reaches 800 degrees Fahrenheit, while the night side drops to -300 degrees Fahrenheit, a temperature difference of 1,100 degrees. This happens because Mercury has virtually no atmosphere to redistribute heat and rotates incredibly slowly. A single day on Mercury lasts 170 Earth days, meaning the sun hangs motionless in the sky for months at a time. Mars has dust storms that can cover the entire planet for months. These global dust storms begin small, but grow until they obscure every surface feature on the planet. The dust is so fine it acts like powder, rising 40 miles into the atmosphere and taking months to settle. During these storms, the planet's surface becomes completely invisible from space, hidden under a uniform brown shroud. What triggers these planet-wide storms remains a mystery. On the dwarf planet Ceres, there are bright white spots that puzzled astronomers for years. These spots turned out to be salt deposits left behind by briny water that erupts from the planet's interior and immediately sublimates into space. Ceres has a subsurface ocean and active geology, essentially making it a giant, frozen, saltwater volcano constantly bleeding its interior into the vacuum of space. Pluto's atmosphere is escaping into space so rapidly that it leaves a tail like a comet. Despite being incredibly cold and distant, Pluto has weather, seasons, and atmospheric dynamics. Its thin nitrogen atmosphere is literally evaporating away, creating a stream of gas that stretches behind the dwarf planet as it orbits. Pluto is slowly bleeding its atmosphere into space, transforming from a world with weather into an airless rock. Uranus rotates on its side, likely due to a massive collision early in its formation. This sideways rotation means that each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. Seasons on Uranus last decades, and the planet's magnetic field tumbles through space as the planet rotates, creating a completely chaotic electromagnetic environment unlike anywhere else in the solar system. The largest volcano in the solar system is on Mars, Olympus. Mons stands 13.6 miles high, nearly 3 times taller than Mount Everest, and covers an area roughly the size of Arizona. This shield volcano is so massive that its weight has actually bent the Martian crust beneath it. Standing on the rim, you couldn't see the base because it would be beyond the horizon. The volcano is so tall that its peak extends above most of Mars' atmosphere. Some moons orbit backwards. Most moons in our solar system formed from the same rotating disk as their parent planet and orbit in the same direction the planet spins. But several moons, including Triton around Neptune and Phoebe around Saturn, orbit backwards. This retrograde motion indicates they were probably captured asteroids or Kuiper belt objects that were gravitationally kidnapped by their planets. Io, Jupiter's volcanic moon, is being turned inside out by gravity. Jupiter's immense gravitational field, combined with the gravitational pull of other large moons, constantly flexes Io's interior, generating enough heat to maintain over 400 active volcanoes. Some of these volcanoes shoot lava 190 miles into space. Io's surface is completely resurfaced by volcanic activity every few thousand years, making it the most geologically active body in the solar system. The most extreme example of planetary madness might be 55 Cancri, a planet where the surface is likely covered in lava and the atmosphere rains liquid rock. This super-Earth orbits so close to its star that its year lasts just 18 hours. One side permanently faces the star, reaching temperatures of 4,000 degrees Fahrenheit, hot enough to vaporize rock. The other side, in eternal darkness, is only 2,000 degrees. The temperature difference likely drives winds of vaporized rock across the planet's surface. These planetary extremes aren't cosmic accidents. They're the natural result of physics operating under different conditions. Each world represents a different experiment in planetary formation, composition, and evolution. They show us that Earth's gentle weather, stable temperatures, and breathable atmosphere aren't just rare. They're miraculous anomalies in a universe where planetary madness is the norm. The more we explore other worlds, the more we realize that Earth isn't just uncommon. It's a cosmic oasis of calm in a universe filled with environmental chaos. Our planet's boring, predictable weather suddenly seems like the most extraordinary thing in the cosmos. Chapter 3. Stellar Chaos. Stars seem peaceful from Earth, gentle points of light twinkling in the night sky. But up close, they're cosmic monsters of violence and destruction, operating on scales that make planetary extremes look gentle by comparison. The stellar universe is a battlefield where the fundamental forces of physics wage war across billions of years. Neutron stars are so dense that a teaspoon of their material would weigh 6 billion tons, roughly equivalent to Mount Everest compressed into a sugar cube. These stellar corpses pack more mass than our Sun into a sphere just 12 miles across. Their gravity is so intense that if you dropped an object from 1 meter high, it would hit the surface traveling at 4 million miles per hour. The surface gravity is 200 billion times stronger than Earth's. But neutron stars don't just sit there being impossibly dense. Some spin up to 700 times per second, faster than a kitchen blender. These millisecond pulsars are among the most precise timekeepers in the universe, more accurate than atomic clocks. PSRJ 1748-2446 AD spins 716 times per second, meaning a point on its equator travels at roughly 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the star's material should fly apart, but it's held together by gravity so strong it warps space itself. Magnetars possess magnetic fields trillions of times stronger than Earth's. If a magnetar were located halfway between Earth and the Moon, its magnetic field would wipe every credit card, hard drive, and magnetic device on the planet. The magnetic field is so powerful, it distorts the shape of atoms, making chemistry impossible near the star's surface. When magnetars have starquakes, sudden shifts in their crust, they release more energy in 1/10 of a second than our Sun produces in 100,000 years. Some stars are so large, they challenge our understanding of stellar physics. Canis Majoris is so enormous that if you replaced our Sun with it, its surface would extend beyond the orbit of Jupiter. Light takes over 8 hours to travel across its diameter. If you could drive a car around its equator at highway speeds, the journey would take 220,000 years. This star contains enough material to build 30 billion suns, yet it's so diffuse that its outer atmosphere is essentially a vacuum by Earth standards. R13601, currently the most massive known star, weighs 315 times more than our Sun and shines 8.7 million times brighter. This monster star burns through its nuclear fuel so rapidly that it loses mass equivalent to Earth's entire mass every single year through stellar winds. The radiation pressure from its core is so intense it's literally blowing itself apart. Stars like this can only exist briefly. They consume their fuel in just a few million years before exploding as hypernovae. Brown dwarfs are failed stars that never quite managed to ignite nuclear fusion. They exist in a twilight zone between the largest planets and the smallest stars. Some brown dwarfs have weather systems with clouds made of molten iron and liquid rock rain. WISE-J 104915.57-531906.1b has atmospheric temperatures that vary by 2,000 degrees Fahrenheit between its day and night sides, creating iron droplet hurricanes that rage across its surface at thousands of miles per hour. Wolf-Rayet stars are cosmic time bombs in their final death throes. These massive stars have blown off their outer hydrogen layers, exposing their nuclear-burning cores directly to space. They shine with the intensity of hundreds of thousands of suns while losing mass at rates that would completely erode our sun in just 100,000 years. WL-104 is pointed almost directly at Earth, 8,000 light-years away. When it explodes as a hypernova, it could potentially strip away our planet's ozone layer with its gamma-ray beam. Binary star systems create gravitational chaos that defies imagination. In some close binary systems, one star literally cannibalizes its companion. The larger star's gravity strips material from its partner, creating an accretion disk of superheated matter spiraling between them. When enough material accumulates, it triggers nova explosions, stellar-scale nuclear bombs that can outshine entire galaxies for weeks. The most violent stellar explosions are gamma-ray bursts, beams of energy so intense they can be seen from the edge of the observable universe. These occur when massive stars collapse into black holes, creating focused beams of radiation that carry more energy than our sun will produce in its entire 10 billion year lifetime. A gamma-ray burst just 1,000 light-years away would strip Earth's atmosphere and sterilize the planet's surface. Variable stars pulse like cosmic lighthouses, changing brightness in predictable patterns. Some Cepheid variables change from bright to dim and back again in periods ranging from days to months. R Lyrae stars pulsate so regularly they're used as cosmic clocks to measure distances across the universe. These stellar oscillations occur because the star's interior is literally unstable. Layers of gas contract and expand in rhythm, causing the entire star to breathe. Some stars appear to violate the laws of stellar evolution. SDSSJ 102-915-172927 contains almost no elements heavier than hydrogen and helium, making it essentially a second-generation star that formed from nearly pristine Big Bang material. According to stellar formation theory, such a star shouldn't be able to form or survive. Yet there it is, challenging our understanding of how the first stars lived and died. Stellar collisions create impossible objects. When two neutron stars merge, they produce kilonova explosions that create most of the universe's gold, platinum, and uranium. These cosmic crashes are so violent they create gravitational waves, ripples in spacetime itself that we can now detect on Earth. The kilonova GW170817 produced more gold than exists in Earth's crust and created heavy elements equivalent to 20,000 Earth masses in just a few seconds. Red hypergent stars, like VV Cephei, are so unstable they constantly erupt material into space. These stellar monsters are caught in a cosmic tug-of-war between their own gravity, trying to hold them together, and radiation pressure trying to blow them apart. They pulsate irregularly, sometimes dimming by factors of hundreds as they eject massive clouds of material into space, then brightening again as they contract. Perhaps strangest of all are zombie stars, white dwarfs that should be dead but keep exploding. These stellar remnants can steal material from companion stars until they reach a critical mass, then explode as Type Ia supernova. But some white dwarfs survive their own explosions and repeat the process. These recurrent novae are stellar phoenixes that die and are reborn in cyclic explosions spanning thousands of years. The stellar universe operates on energy scales that dwarf anything in human experience. A single supernova releases more energy than a trillion nuclear weapons exploding every second for millions of years. Yet this violence is creative. Stars forge every element in your body except hydrogen. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces and distributed by stellar explosions. When you look up at stars, you're not seeing peaceful lights in the sky. You're witnessing the most violent, energetic, and creative processes in the universe. Each star is a nuclear reactor millions of times more powerful than anything humans have ever built, sustained by forces that could tear apart planets. The gentle twinkling is just distance making monsters look beautiful. Chapter 4: Galactic Mysteries. Beyond the chaos of individual stars lies an even stranger realm. Entire galaxies that operate according to principles that challenge our understanding of physics, time, and the very structure of reality. When billions of stars organize into galactic structures, the resulting phenomena exceed the merely impossible and enter the realm of the cosmically absurd. Our own Milky Way galaxy is cannibalistic. Right now, it's in the process of devouring at least 15 smaller galaxies. The Sagittarius dwarf galaxy is being stretched like cosmic taffy as our galaxy's gravity tears it apart, creating streams of stars that wrap around the Milky Way multiple times. We're also on a collision course with the Andromeda Galaxy, our nearest large neighbor. In roughly 4.5 billion years, these two galaxies will merge in a slow-motion cosmic car crash that will completely reshape both structures. The center of our galaxy harbors a supermassive black hole called Sagittarius, an asterisk that weighs 4.3 million times more than our Sun. This monster is surprisingly quiet most of the time, but occasionally it flickers to life when something falls into it. In 2019, astronomers watched it suddenly brighten to 75 times its normal luminosity as it consumed something, possibly a large asteroid or small planet. The black hole literally ate something the size of a small world, and we watched it happen in real time. Some galaxies rotate backwards compared to their neighbors, suggesting they've had violent histories. NGC 4622 spins in the opposite direction to what its spiral arms suggest it should, likely because it collided with another galaxy and had its rotation reversed by the gravitational interaction. These backwards galaxies are cosmic fossils that preserve evidence of ancient galactic violence. Ultra-diffuse galaxies challenge our understanding of how galaxies form. These ghostly structures are as large as the Milky Way, but contain only 1% as many stars, making them so faint they're nearly transparent. Dragonfly 44 is almost entirely dark matter. 99.99% of its mass comes from invisible material that only interacts gravitationally. It's essentially a galaxy-sized cloud of dark matter with just enough normal matter to make a few scattered stars visible. Active galactic nuclei are galaxies with supermassive black holes that are actively feeding. These create the most luminous objects in the universe, quasars that can outshine the combined light of a trillion stars. 3C273 is so bright that despite being 2.5 billion light-years away, it appears as bright as a 13th magnitude star through a telescope. The energy comes from matter spiraling into the central black hole, heating to billions of degrees and creating jets of particles that extend for millions of light-years. Some galaxies are connected by invisible bridges of dark matter, Computer simulations suggest that galaxies exist within a cosmic web of dark matter filaments. But in 2012, astronomers found direct evidence: a bridge of dark matter connecting the galaxy clusters Abell 222 and Abell 223. This bridge stretches 18 million light-years across space, roughly 180 times the diameter of the Milky Way, and contains no visible matter, only the gravitational effects of dark matter. Elliptical galaxies are cosmic mysteries that shouldn't exist according to simple galaxy formation models. These smooth, featureless galaxies show little sign of active star formation, yet they're among the most massive galaxies in the universe. M87 contains 2.7 trillion stars and has a supermassive black hole with a mass of 6.5 billion suns. The galaxy is so large that light takes 120,000 years to cross from one side to the other. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, is being slowly destroyed by our galaxy's gravity. As it orbits us, its gas and stars are being stripped away, creating the Magellanic Stream, a trail of hydrogen gas that stretches halfway around the sky. This stream is evidence of galactic cannibalism happening in slow motion over hundreds of millions of years. Some galaxies have no dark matter at all, which shouldn't be possible. NGC 1052 DF2 contains roughly as much dark matter as our solar system, virtually none for a galaxy of its size. This discovery challenges the standard model of galaxy formation, which requires dark matter to provide the gravitational scaffolding for normal matter to collect into galactic structures. A galaxy without dark matter is like a building without a foundation. Starburst galaxies are experiencing explosive periods of star formation that consume their gas reserves thousands of times faster than normal. The antennae galaxies are colliding and triggering star formation at such a rapid rate that they're creating star clusters, more massive than any known in the Milky Way. These cosmic baby booms are so intense they'll exhaust the galaxies, star-forming material in just a few million years. The Hubble Ultra Deep Field revealed that the early universe was filled with bizarre, asymmetric galaxies unlike anything we see today. These ancient galaxies, seen as they appeared when the universe was young, are chaotic, irregular structures that look nothing like the neat spirals and ellipticals in our cosmic neighborhood. They suggest that galaxy formation was a much more violent and unpredictable process in the early universe. Some galaxies are moving away from us faster than the speed of light due to the expansion of space itself. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying them away from us. The most distant observed galaxy, GNZ11, is receding from us at roughly 2.3 times the speed of light. We see it as it appeared when the universe was only 400 million years old. Ring galaxies are cosmic accidents created by galactic collisions. Hoag's object is a nearly perfect ring of stars surrounding a bright central nucleus with almost nothing in between. This bizarre structure likely formed when a smaller galaxy passed through the center of a larger spiral galaxy, creating gravitational waves that reorganized the stars into a ring. The process is so rare that only a few hundred ring galaxies are known to exist. The Perseus galaxy cluster contains a supermassive black hole that has been singing the same note for 2.5 billion years. The black hole creates pressure waves in the hot gas surrounding it, generating sound waves with a frequency 57 octaves below middle C, the deepest note ever detected in the universe. This cosmic bass note has been playing continuously since before Earth formed. Some galaxies exist in cosmic voids, vast empty regions of space with almost no matter. These void galaxies are cosmic hermits, isolated by hundreds of millions of light years from their nearest neighbors. They challenge our understanding of galaxy formation because they exist in regions where there shouldn't be enough matter to form galaxies at all. Galaxy clusters themselves are surrounded by enormous halos of dark matter that extend far beyond the visible galaxies. The Coma cluster, containing over 1,000 galaxies, is embedded in a dark matter halo that stretches over 20 million light-years across. This invisible structure contains 10 times more mass than all the visible galaxies combined, yet we can only detect it through its gravitational effects. Perhaps most mysteriously, some galaxy clusters are moving in coordinated directions across cosmic distances, suggesting the influence of structures beyond our observable horizon. The dark flow appears to be pulling galaxy clusters toward a specific region of space, possibly indicating the gravitational influence of matter beyond the edge of the visible universe. These galactic mysteries remind us that individual stars and planets, however strange, are just components and structures that operate on scales where our normal concepts of cause and effect break down. Galaxies live and die, collide and merge, birth and devour each other across billions of years in a cosmic drama that makes stellar violence look peaceful by comparison. When you consider that our entire solar system is just one tiny component in this galactic madhouse, the perspective shift is profound. We're not just residents of a strange planet orbiting a violent star. We're passengers on a cosmic structure that's simultaneously eating its neighbors and racing toward an inevitable collision, all while riding waves of invisible dark matter through an expanding universe. Chapter 5: Universal Extremes. As vast as galaxies are, they're merely islands in an ocean of space that contains phenomena so extreme they redefine the meaning of impossible. At the largest scales, the universe reveals behaviors that make galactic violence look gentle and suggest that reality itself operates according to principles that barely qualify as physics. The observable universe contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars. But here's what makes this truly mind-bending. This might represent less than 5% of what actually exists. The rest of the universe beyond our cosmic horizon could be infinite, containing unlimited copies of every possible configuration of matter. There might be infinite versions of you reading infinite versions of this sentence right now. Dark energy is accelerating the expansion of space itself at an ever-increasing rate. Not only is the universe expanding, but that expansion is speeding up. Space itself is being created at such a rapid rate that distant galaxies are moving away from us faster than light. In roughly 100 billion years, cosmic expansion will have carried all other galaxies beyond our observable horizon, leaving the Milky Way alone in an apparently empty universe. The cosmic microwave background radiation tells us that the universe was once hot and dense enough that atoms couldn't exist. For the first 380,000 years after the Big Bang, the universe was a glowing plasma soup so hot that electrons couldn't stay bound to atomic nuclei. When it finally cooled enough for atoms to form, the universe became transparent for the first time. And we can still see the glow from that moment as microwave radiation coming from every direction in space. Empty space isn't actually empty. It's filled with quantum fields that constantly create particle pairs from nothing, only to have them annihilate each other almost instantly. This quantum foam means that at the smallest scales, space is a roiling sea of creation and destruction, happening trillions of times per second. The vacuum of space contains infinite energy, held in check only by the brief lifetime of virtual particles. The universe has a temperature, and it's getting colder. The cosmic background temperature is currently 2.7 Kelvin, just barely above absolute zero. As the universe continues expanding, this temperature will continue dropping. In about 1 trillion years, the cosmic background will be so cold that it will be colder than the surface of the coldest stars, making the universe's background environment more hostile to life than the space between galaxies is today. Cosmic inflation suggests that in the first fraction of a second after the Big Bang, Space expanded faster than light by a factor of at least 1026. During this period, a region smaller than a proton grew to larger than a grapefruit almost instantaneously. This inflation period happened so quickly that it could have created our entire observable universe from quantum fluctuations smaller than atomic nuclei. The largest structure in the known universe is the Hercules Corona Borealis Great Wall, a supercluster of galaxies stretching 10 billion light-years across, roughly 10% of the diameter of the observable universe. This structure is so large that light hasn't had time to cross it since the Big Bang. It shouldn't exist according to the standard model of cosmology. Yet there it is, challenging our understanding of how the universe evolved. Black holes warp space and time so severely that they create regions where the normal rules of physics break down completely. At the event horizon, time dilation becomes infinite. From the outside perspective, anything falling in appears to freeze at the boundary and fade away. But from the falling object's perspective, it passes through normally and gets crushed by infinite gravity at the singularity, where density becomes infinite and space-time curvature becomes undefined. The Big Rip is a possible future scenario where dark energy eventually overcomes all other forces in the universe. If dark energy continues accelerating expansion, it will eventually grow strong enough to overcome gravity, electromagnetic forces, and even nuclear forces. First, galaxy clusters will separate, then galaxies will disperse, then solar systems will break apart, then planets will dissolve, and finally atoms themselves will be torn apart as space expands faster than the forces that hold matter together can operate. Cosmic strings, if they exist, would be one-dimensional defects in spacetime itself, infinitesimally thin lines of pure energy that could stretch across the entire universe. A cosmic string passing near Earth would create gravitational effects so severe it could split the planet in half. Yet the string itself would be thinner than a proton. These hypothetical objects would be the most extreme example of energy density in the universe. The multiverse hypothesis suggests that our universe might be just one bubble in an infinite cosmic foam where every possible variation of physical laws plays out. There might be universes where electrons are positively charged, where gravity repels instead of attracts, where there are different numbers of spatial dimensions, or where time runs backwards. If true, every possible history and future exists somewhere in the infinite ensemble of realities. Baryon acoustic oscillations are fossilized sound waves from the early universe that have been stretched by cosmic expansion into patterns we can still observe today. These acoustic peaks in the cosmic microwave background represent pressure waves that traveled through the hot plasma of the early universe, creating a cosmic echo that reveals the universe's composition and geometry. The horizon problem reveals that opposite sides of the observable universe have exactly the same temperature, despite never having been in causal contact. Light from one edge of the cosmic microwave background has never had time to reach the other edge, yet they show the same temperature to within 0.0001 degrees. This suggests either faster-than-light communication in the early universe, or that our observable universe is just a tiny, uniform patch of a much larger cosmic structure. Dark matter outweighs normal matter by a factor of 5 to 1, yet we don't know what it is. This invisible material only interacts gravitationally. It doesn't emit, absorb, or reflect light. Dark matter particles are constantly passing through your body by the trillions, but they interact so weakly with normal matter that you never notice. The universe is mostly made of something completely unknown to science. The flatness problem shows that the universe is balanced on a knife's edge between eternal expansion and gravitational collapse. The actual density of the universe is within 0.4% of the critical density needed for flat spacetime. This incredible fine-tuning suggests either remarkable cosmic coincidence or underlying physics we don't understand. Cosmic rays are atomic nuclei accelerated to nearly the speed of light by unknown cosmic phenomena. The most energetic cosmic rays carry more energy than a fastball baseball compressed into a single atomic nucleus. These ultra-high energy particles shouldn't be able to reach Earth from distant sources because they would interact with cosmic microwave background radiation. Yet they arrive anyway, suggesting unknown acceleration mechanisms operating in the universe. The anthropic principle observes that the fundamental constants of physics are fine-tuned for the existence of complex matter and life. If the strong nuclear force were slightly weaker, atoms would fall apart. If it were slightly stronger, hydrogen couldn't exist. The electromagnetic force, gravitational constant, and other fundamental values all fall within extremely narrow ranges that allow chemistry, stars, and planets to exist. Time itself might have a beginning and end. The Big Bang represents not just the beginning of matter and energy, but potentially the beginning of time itself. Before the Big Bang, there might not have been a before. Similarly, as the universe expands and cools, entropy increases toward a maximum state where no further change is possible, the heat death of the universe when time itself becomes meaningless. These universal extremes remind us that our entire experience of reality, matter, energy, space, and time might be temporary features of a cosmic environment that's fundamentally alien to everything we consider normal. We exist during a brief period when the universe happens to support complex structures, in a tiny region where physics operates according to rules that allow consciousness to emerge. The universe is not just stranger than we imagine. It might be stranger than we can imagine. Every extreme we discover reveals new questions about the nature of existence itself. Chapter 6: Quantum Space. At the smallest scales of reality, space itself becomes a quantum phenomenon where the normal rules of physics dissolve into probability clouds and impossible behaviors. Quantum mechanics in space reveals that the universe operates on principles so strange they challenge our most basic assumptions about existence, causality, and the nature of reality itself. Quantum entanglement creates spooky action at a distance that Einstein famously rejected, but experiments have repeatedly confirmed. When two particles become entangled, measuring one instantly affects the other regardless of the distance separating them. This connection operates faster than light, is instantaneous across any distance. Entangled particles have been separated by thousands of miles on Earth, and the connection remains perfect. In space, quantum entanglement could theoretically connect particles across galaxies, creating a cosmic web of instantaneous quantum communication. The quantum vacuum isn't empty. It's a seething foam of virtual particles constantly appearing and disappearing. These quantum fluctuations create measurable effects like the Casimir force, where empty space between two conducting plates actually pushes them together. In space, quantum vacuum fluctuations might be responsible for dark energy and cosmic inflation. The empty space between galaxies is actually filled with quantum activity operating below the threshold of direct observation. Zero-point energy exists even at absolute zero temperature, meaning that motion never completely stops even when thermal energy is removed. This residual quantum motion persists in all matter throughout the universe. Even in the coldest regions of interstellar space, atoms continue vibrating due to quantum uncertainty. This quantum motion might provide the energy needed for various cosmic processes and could potentially be harvested as an unlimited energy source. Quantum tunneling allows particles to pass through barriers that should be impenetrable according to classical physics. In space, this enables nuclear fusion in stellar cores at temperatures that shouldn't be sufficient to overcome electromagnetic repulsion. Quantum tunneling is literally what keeps stars burning. Without it, nuclear fusion would require much higher temperatures, and most stars, including our Sun, couldn't sustain nuclear reactions. The uncertainty principle means that space and time themselves become fuzzy at quantum scales. At distances smaller than the Planck length 1035 meters, the concepts of precise location and duration break down completely. Space becomes a quantum foam where geometry itself fluctuates. Time becomes uncertain, with virtual timelines branching and merging. At these scales, the smooth space-time of general relativity gives way to a choppy quantum sea. Quantum superposition allows particles to exist in multiple states simultaneously until observed. In space, this means that quantum systems can be in multiple configurations at once. A quantum satellite could theoretically be in multiple orbits simultaneously until someone measures its position. Superposition breaks down when quantum systems interact with their environment, a process called decoherence. But in the near-perfect vacuum of space, superposition effects could persist much longer than on Earth. Virtual particles created by quantum fluctuations can become real under extreme conditions. Near black holes, the intense gravitational field can separate virtual particle pairs, preventing them from annihilating each other. This process, called Hawking radiation, means that black holes slowly evaporate by converting virtual particles into real ones. The stranger the space-time geometry, the more likely virtual particles are to become permanent additions to reality. Quantum field theory suggests that all particles are actually excitations in underlying quantum fields that permeate all of space. The electron field fills every cubic centimeter of the universe, and what we call electrons are simply waves in this field. Empty space is actually filled with all possible quantum fields in their lowest energy states. What we perceive as solid matter is really just patterns of excitation in quantum fields that exist everywhere. Quantum coherence in space could enable phenomena impossible on Earth. Large-scale quantum effects become possible when systems are isolated from environmental interference. Some theories suggest that entire celestial bodies could maintain quantum coherence under certain conditions, leading to macroscopic quantum effects like superposition of planetary orbits or quantum entanglement between distant astronomical objects. The quantum Zeno effect occurs when frequent observations prevent quantum systems from evolving. In space, where observation and measurement are rare, quantum systems could evolve in ways impossible in observed laboratory conditions. This might allow for exotic quantum states that persist for cosmic time periods, creating quantum structures on astronomical scales. Quantum phase transitions can occur in extremely cold regions of space, where matter exists in exotic quantum states. Bose-Einstein condensates, where thousands of atoms behave as a single quantum entity, could form naturally in the coldest regions between stars. These quantum fluids might exhibit properties like superfluidity and superconductivity on cosmic scales. The many worlds interpretation of quantum mechanics suggests that every quantum measurement splits the universe into multiple parallel realities. If true, space is constantly branching into countless parallel universes where every possible outcome of every quantum event plays out. The cosmic microwave background might preserve evidence of quantum choices made in the early universe, creating a fossil record of quantum branching events. Quantum information processing in space could operate without the limitations imposed by Earth's environment. Quantum computers in the vacuum of space could maintain coherence for extended periods, potentially solving computational problems that require cosmic timescales. The absence of atmospheric interference and thermal noise could enable quantum calculations impossible on planetary surfaces. Entanglement between photons can create quantum communication networks across space. NASA has already demonstrated quantum communication between Earth and satellites. Future quantum communication networks could connect spacecraft across the solar system using entangled photons, creating unhackable communication channels that operate instantaneously regardless of distance. Quantum gravity effects become important near black holes and during the first moments after the Big Bang. At these extremes, space and time themselves become quantum phenomena subject to superposition and uncertainty. The smooth geometry of space-time dissolves into quantum foam, and the distinction between space, time, and matter breaks down completely. Spontaneous symmetry breaking in quantum fields might explain why the universe has the particular properties we observe. The Higgs field, which gives particles their mass, exists in a state that breaks the fundamental symmetry of physics. Other quantum fields might be responsible for breaking symmetries that determine the number of spatial dimensions, the direction of time, and the fundamental constants of nature. Quantum fluctuations in the early universe might have created the seeds of all cosmic structure. Tiny quantum variations in density, stretched by cosmic inflation, could have grown into the galaxies and galaxy clusters we see today. This means that every star, planet, and living being owes its existence to quantum uncertainty in the first fraction of a second after the Big Bang. Quantum error correction occurs naturally in some physical systems, suggesting that the universe might be actively protecting quantum information from destruction. This quantum Darwinism could explain how classical reality emerges from quantum foundations and why certain quantum states persist while others decay. Laboratory experiments with quantum systems in space reveal behaviors impossible under Earth conditions. The Cold Atom Laboratory on the International Space Station creates Bose-Einstein condensates that last much longer than possible on Earth, allowing researchers to study quantum effects that only become apparent over extended time periods. These quantum space phenomena suggest that reality, at its most fundamental level, operates according to principles that seem to violate our everyday experience of cause and effect, locality, and deterministic behavior. The universe isn't just strange at large scales. It's built from quantum strangeness at the smallest scales. And this quantum foundation influences everything from stellar fusion to cosmic evolution. Understanding quantum space means recognizing that the boundary between possible and impossible is itself a quantum phenomenon, subject to probability rather than certainty. In a quantum universe, the impossible isn't forbidden. It's just improbable. And given enough space and time, even the improbable becomes inevitable. Chapter 7. Time Paradoxes. Time in space doesn't behave like time on Earth. Einstein's theories revealed that time is relative, malleable, and far stranger than our daily experience suggests. In the cosmic environment, time dilates, contracts, stops, and sometimes seems to run backwards, creating paradoxes that challenge our most basic understanding of causality and existence. Gravitational time dilation means that time literally runs slower in stronger gravitational fields. On Earth, this effect is tiny but measurable. Atomic clocks run slightly slower at sea level than on mountaintops. But near massive objects in space, the effects become extreme. An astronaut orbiting close to a black hole would age much slower than someone on Earth. Near the event horizon of a supermassive black hole, 1 hour could equal 7 years on Earth. The difference depicted in the movie Interstellar is actually based on real physics. GPS satellites experience time differently than people on Earth's surface and must constantly adjust for relativistic effects. The satellites orbit in weaker gravity than Earth's surface, so their clocks run slightly faster, gaining about 38 microseconds per day. Without correcting for this time difference, GPS systems would accumulate errors of about 6 miles per day. Every time you use GPS navigation, your phone is performing relativistic calculations to account for the fact that time runs differently in orbit. Velocity time dilation occurs when objects travel at high speeds relative to each other. At 90% the speed of light, time slows by a factor of 2.3. 1 year for the traveler equals 2.3 years for a stationary observer. At 99% light speed, time slows by a factor of 7. This creates the famous twin paradox. If one twin travels to a nearby star at near-light speed, they could return to find their sibling has aged decades while they've aged only a few years. Some regions of space create closed time-like curves where cause and effect become circular. Rotating black holes, called Kerr black holes, drag space-time around with them so severely that they create regions where traveling in a straight line through space actually curves back in time. Theoretical physicist Kip Thorne demonstrated that certain configurations of wormholes could allow time travel, though the energy requirements make such scenarios practically impossible. Time stops completely at black hole event horizons from an outside perspective. As you watch something fall toward a black hole, it appears to slow down and freeze at the horizon, its light redshifting until it fades away. But from the falling object's perspective, time continues normally as it crosses the horizon and approaches the singularity. The same event crossing the event horizon happens and doesn't happen simultaneously, depending on your reference frame. Cosmic jets from quasars appear to travel faster than light, creating an apparent violation of causality called superluminal motion. These jets actually travel at about 99% light speed, but because they're pointed almost directly at Earth, the light they emit at different times arrives almost simultaneously, creating the illusion that they're overtaking their own light. This shows how the finite speed of light can create temporal illusions across cosmic distances. The expansion of space itself affects the flow of time. In regions where space expands rapidly, such as during cosmic inflation, time becomes ill-defined. The boundaries between past, present, and future blur when space-time itself is changing faster than light can propagate. This suggests that time might have been created during the Big Bang rather than existing as a pre-existing framework for events. Tidal forces near massive objects create time gradients where different parts of the same object experience time at different rates. Near a black hole, your head and feet would age at measurably different rates, an effect called spaghettification. Over time, these temporal gradients would stretch your body as gravity literally pulls your future apart. Cosmic strings, if they exist, could create spectacular time effects. These hypothetical one-dimensional objects would be so massive that they significantly warp spacetime. A cosmic string moving at high speed could create a configuration where you could travel around it and return to your starting point before you left, essentially creating a time machine through gravitational manipulation of spacetime geometry. The cosmic microwave background preserves light that has been traveling for 13.8 billion years, essentially allowing us to see the past directly. We observe the universe as it existed when it was only 380,000 years old. But due to cosmic expansion, the regions we're observing are now much farther away than they were when the light was emitted. We're simultaneously looking 13.8 billion years into the past and 46 billion light years into space. Redshift effects cause distant galaxies to appear younger than they actually are. Light from these galaxies has been stretched by cosmic expansion, shifting toward longer wavelengths. This redshift affects not just the color of light, but also the apparent rate of time. Distant supernovae appear to explode in slow motion because the expansion of space stretches the time intervals between photons arriving at Earth. Frame dragging effects near rotating massive objects literally twist spacetime, causing gyroscopes to precesses and affecting the flow of time in direction-dependent ways. The Earth's rotation creates measurable frame-dragging effects that have been detected by satellite experiments. Near rotating black holes, frame dragging becomes so extreme that it's impossible to remain stationary relative to distant stars. Space itself is being dragged around the black hole. Oh, isn't stationary relative to distant stars. Space itself is being dragged around the black hole. Wormholes could theoretically connect different moments in time as well as different locations in space. A traversable wormhole might link today's Earth to Earth a million years in the future, creating a temporal portal. However, the exotic matter required to keep wormholes open has negative energy density, something that might not exist in nature. The arrow of time, the fact that time seems to have a preferred direction, becomes ambiguous in some cosmic scenarios. Near black holes, the distinction between space and time coordinates becomes blurred. Inside a black hole, the radial direction becomes time-like, while time becomes space-like, essentially meaning that falling toward the singularity becomes inevitable in the same way that moving forward in time is inevitable for us. Quantum effects can create temporal paradoxes on cosmic scales. The quantum Zeno effect suggests that frequent observation can prevent quantum systems from evolving, essentially stopping time for quantum processes. In the vacuum of space, where observation is rare, quantum systems might evolve according to different temporal rules than those we observe in laboratories. Cosmic time isn't universal. There's no absolute now for the entire universe. Events that appear simultaneous from one reference frame occur at different times when observed from another frame moving at high speed. This relativity of simultaneity means that the universe doesn't have a universal present moment. The Big Bang didn't happen at the same time everywhere. It happened at different cosmic times, depending on your reference frame. Dark energy's acceleration of cosmic expansion affects the global flow of time. As space expands faster, the relationship between cosmic time and local time becomes increasingly complex. In the far future, when cosmic expansion has carried all other galaxies beyond our observable horizon, the relationship between local time and cosmic time might become completely disconnected. Primordial black holes, if they exist, could have formed shortly after the Big Bang and would now be exploding due to Hawking radiation. These explosions would create temporal paradoxes because the black holes would simultaneously exist and not exist. Their formation would be a past event, but their evaporation would erase them from history, creating closed causal loops. Time travel to the past might be possible using quantum mechanics and curved spacetime. Some interpretations of quantum mechanics suggest that information can travel backward in time under certain conditions. Combined with the curved spacetime near massive objects, this might allow limited forms of retroactive causality, where effects can precede their causes. These temporal paradoxes reveal that time isn't the steady, universal constant we experience on Earth. Time is a dynamic, malleable dimension that responds to mass, energy, gravity, and motion in ways that create genuine paradoxes and impossibilities. In space, yesterday, today, and tomorrow become relative concepts that depend entirely on where you are and how fast you're moving. The most unsettling implication might be that the universe doesn't have a single consistent timeline. Instead, it contains countless overlapping temporal reference frames where events occur in different orders, where cause and effect become circular, and where the very concept of when becomes meaningless. We don't just live in space, we live in space-time, and time itself is far stranger than space. Chapter 8. Alien Physics. Beyond the extremes of normal space lie regions where physics itself behaves so strangely that familiar concepts like matter, energy, and causality break down completely. These are realms where the universe experiments with alternative rules of reality, creating phenomena so alien to our experience that they challenge whether we understand physics at all. Negative mass, while theoretically possible, would create gravitational effects that repel. If negative mass exists in space, it would fall upward in gravitational fields and push other objects away gravitationally. A pair of positive and negative masses would chase each other in perpetual acceleration, with the positive mass running from the negative mass that's pushing it away while the negative mass chases the positive mass that's pulling it. This violates our intuition about conservation of energy and momentum. Exotic matter with negative energy density might exist in quantum fields, creating regions of space where energy is less than zero. This exotic matter could theoretically hold open traversable wormholes and enable faster-than-light travel through space-time shortcuts. The Alcubierre drive concept requires exotic matter to contract space in front of a spacecraft and expand it behind, allowing the ship to travel faster than light without actually moving through space. Strange quark matter could exist in the cores of neutron stars, creating a form of matter more stable than ordinary atomic matter. If strange matter is truly stable, it could convert normal matter on contact, turning entire planets into strange matter objects. A tiny piece of strange matter falling to Earth could potentially convert our entire planet into a dead, ultra-dense sphere of exotic quarks. Monopoles are hypothetical particles with only one magnetic pole, north or south, but not both. If magnetic monopoles exist, they would fundamentally alter electromagnetic theory and could explain why electric charge comes in discrete units. Grand unified theories predict that monopoles should exist, yet none have ever been found despite decades of searching. If they exist in space, they would create magnetic fields unlike anything in terrestrial physics. Dark photons are hypothetical particles that interact with dark matter but barely interact with ordinary matter. These hidden sector particles could if dark photons exist, there could be an entire parallel physics operating alongside normal physics but remaining invisible to our instruments. Tachyons are hypothetical particles that always travel faster than light. If they exist, tachyons could theoretically transmit information backward in time, creating causality paradoxes. While no evidence for tachyons exists, they aren't explicitly forbidden by relativity theory. Mirror matter is a hypothetical form of matter composed of mirror particles that interact with ordinary matter only through gravity. Mirror atoms, mirror chemistry, and mirror biology could exist alongside our universe, but remain completely invisible except for gravitational effects. Mirror matter could explain dark matter and might form mirror planets, mirror stars, and mirror life that coexists with our reality. Vacuum decay is a terrifying possibility where the Higgs field could spontaneously transition to a lower energy state, fundamentally altering the laws of physics throughout the universe. This phase transition would propagate outward at the speed of light, destroying everything in its path by changing the masses of particles and the strength of forces. The altered physics might not allow atoms, chemistry, or life to exist. Extra dimensions beyond the familiar three spatial dimensions could exist, but remain hidden at microscopic scales. String theory requires additional spatial dimensions that could be curled up so small we can't detect them. Alternatively, we might be trapped on a three-dimensional brane floating in a higher dimensional space. Gravity might leak into these extra dimensions, explaining why it's so much weaker than other fundamental forces. Quantum foam at the Planck scale might reveal that space-time itself is quantized rather than continuous. At distances of 10 to 35 meters, space and time could consist of discrete units rather than smooth geometry. This would mean that reality is topological defects in spacetime could create regions where the normal rules of physics don't apply. Domain walls, cosmic strings, and texture defects might preserve conditions from phase transitions in the early universe. These defects could have exotic properties like negative tension, infinite density, or the ability to create closed time-like curves. Non-commutative geometry suggests meaning that this would make the very concept of precise location meaningless and could explain quantum uncertainty as a fundamental property of space itself rather than just a limitation of measurement. If supersymmetry exists but is broken at accessible energies, it can explain dark matter and solve several problems in particle physics. The light quantum gravity effects near the Planck scale could create spacetime foam, where virtual black holes constantly form and evaporate, making space itself a chaotic quantum system. At these scales, the distinction between matter, energy, space, and time breaks down completely. Reality becomes a probabilistic quantum process where even the dimension of space fluctuates. Violation of Lorentz invariance could occur under extreme conditions, meaning that the speed of light might not be constant for all observers. Some quantum gravity theories predict that space-time itself has a preferred reference frame, violating one of the fundamental principles of relativity. High-energy cosmic ray observations might reveal subtle violations of Lorentz symmetry. Emergent gravity theories suggest that gravity might not be a fundamental force, but rather an emergent property of more basic quantum information processes. Just as temperature emerges from molecular motion, gravity might emerge from quantum entanglement and information theory. This would mean that space-time itself is not fundamental, but emerges from deeper quantum information processes. Holographic principles suggest that all information in a volume of space can be encoded on its boundary surface. This means that three-dimensional space might be an illusion created by information stored on a two-dimensional surface. The universe might literally be a hologram projected from its boundary, making our perception of three-dimensional space a fundamental misunderstanding of reality's true nature. Causal dynamical triangulation attempts to construct space-time from fundamental quantum building blocks, suggesting that space and time emerge from quantum geometry. At the smallest scales, space-time might consist of tiny triangular pieces that can be assembled in different ways, creating the illusion of smooth geometry at larger scales. Black hole complementarity proposes that information falling into a black hole exists both inside the black hole and on its surface simultaneously. This violates the quantum mechanical principle that information cannot be duplicated, creating paradoxes about the nature of information and reality near black holes. Quantum error correction in holographic systems suggests that space-time itself might be an error-correcting code that protects quantum information from destruction. This would mean that the geometry of space emerges from the universe's need to preserve information, making space itself a kind of cosmic hard drive. These alien physics phenomena remind us that our understanding of natural law might be severely limited by our terrestrial perspective. The universe might operate according to principles so strange that they would be incomprehensible to minds evolved in Earth's gentle environment. What we call the laws of physics might just be local bylaws that happen to apply in our cosmic neighborhood. In other regions, under different conditions or at different scales, the universe might experiment with entirely different rules of reality. The most disturbing possibility is that we might be fundamentally unable to understand the true physics of the universe. Our brains evolved to understand medium-sized objects moving at moderate speeds in weak gravitational fields. The actual rules governing reality might be so alien to our evolved intuitions that we can never truly comprehend them. Yet somehow, despite operating in this universe of alien physics, consciousness emerged. Life found a way to exist and evolve in a cosmos governed by rules that seem designed to prevent stable complexity. Perhaps the most alien physics of all is the emergence of beings capable of wondering about the strangeness of their own existence. Chapter 9. Future Horizons. The future of space holds phenomena and possibilities that stretch beyond current physics into realms of speculation that might prove to be inevitabilities. As we look forward across cosmic time, the universe's evolution promises events and transformations that will make current space phenomena look familiar by comparison. The collision between the Milky Way and Andromeda galaxies will begin in approximately 4.5 billion years, creating a spectacular merger that will fundamentally reshape our cosmic neighborhood. Computer simulations show that this collision will trigger massive bursts of star formation as gas clouds compress and collapse. Our solar system will likely be flung to a different position within the merged galaxy, potentially moving from the outer spiral arm to the galactic center, or even being ejected into intergalactic space entirely. Stellar evolution will transform the night sky beyond recognition. Red dwarf stars, which make up 75% of all stars, will continue burning for trillions of years, long after stars like our Sun have died. In 5 billion years, our Sun will expand into a red giant, potentially consuming Mercury and Venus before ejecting its outer layers to create a planetary nebula. The white dwarf remnant will slowly cool over hundreds of billions of years until it becomes a cold, dark cinder. The far future holds the era of stellar mass black holes, beginning around 1034 years from now. By this time, all normal stars will have exhausted their fuel and died. The universe will be dominated by black holes, neutron stars, white dwarfs, and scattered planets. The only sources of energy will be the slow decay of protons, black hole evaporation, and the occasional collision between stellar remnants. Black hole evaporation through Hawking radiation will eventually erase even the most massive black holes. Supermassive black holes containing billions of solar masses will take approximately 10,100 years to completely evaporate. As they shrink, they will actually get hotter, eventually becoming so energetic that they explode in final bursts of gamma rays. These will be among the last energetic events in the universe's history. Proton decay, if it occurs as predicted by some theories, will begin dismantling atoms themselves around 1034 years from now. Even the most stable matter will slowly dissolve as protons spontaneously transform into lighter particles. This process will gradually erase all complex matter in the universe, leaving only electrons, positrons, neutrinos, and photons scattered across ever-expanding space. Heat death represents the universe's final state when entropy reaches its maximum value. All energy will be evenly distributed across space, eliminating the temperature differences necessary to perform work. No stars will shine. No planets will orbit, no chemical reactions will occur. The universe will consist of a thin gas of elementary particles at a temperature just barely above absolute zero, with no structure or activity of any kind. But even heat death might not be final. Quantum mechanics suggests that random fluctuations could eventually recreate complex structures through pure chance. Given infinite time, quantum tunneling could spontaneously reverse entropy, creating brief moments of order in the cosmic chaos. These Poincare occurrences might recreate galaxies, stars, planets, and even life through random quantum events. Vacuum metastability presents a more immediate existential threat. The Higgs field might exist in a false vacuum state that could spontaneously tunnel to a lower energy configuration, fundamentally altering the laws of physics throughout the universe. This vacuum decay would propagate at light speed, destroying everything in its path by changing particle masses and force strengths. Artificial intelligence and space exploration could transform cosmic evolution in ways that transcend biological limitations. Advanced civilizations might learn to manipulate stellar evolution, harvest energy from black holes, or even prevent proton decay through unknown technologies. Intelligence could become the dominant force shaping cosmic evolution, potentially reversing entropy on galactic scales. Terraforming technologies might allow future civilizations to create habitable worlds from barren planets, moons, and asteroids. Mars could be given a thicker atmosphere and warmer temperatures through greenhouse gas release or solar mirrors. Europa's subsurface ocean could be accessed and potentially warmed to create an aquatic world. Even free-floating planets in interstellar space might be made habitable using fusion reactors and enclosed atmospheres. Generation ships could carry Earth life to distant star systems over journeys lasting thousands of years. These vast spacecraft would essentially be artificial worlds supporting entire ecosystems during interstellar voyages. Advanced closed-loop life support systems would recycle air, water, and nutrients indefinitely while maintaining genetic diversity in small populations across many generations. Faster than light travel, while prohibited by relativity, might become possible through exotic physics or space-time manipulation. Alcubierre drives could contract space in front of spacecraft and expand it behind them, allowing effective faster-than-light travel without violating relativity. Traversable wormholes could create shortcuts through higher dimensional space, enabling instantaneous travel across cosmic distances. Megastructures like Dyson spheres could harness the total energy output of entire stars. Advanced civilizations might surround stars with solar collection arrays, capturing virtually all stellar energy for technological purposes. These structures would be visible as infrared signatures from interstellar distances and might already exist around distant stars, waiting for our technology to advance enough to detect them. Space elevators and orbital rings could make space access as routine as air travel. Carbon nanotube cables extending from Earth's surface to geostationary orbit could carry cargo and passengers to space using only the energy needed to power electric motors. Orbital rings around planets could support massive space habitats, housing billions of people in artificial gravity environments. Asteroid mining could provide unlimited material resources for space-based civilizations. A single metallic asteroid contains more platinum than has ever been mined on Earth. The asteroid belt contains enough material to build space habitats supporting trillions of people. Automated mining systems could transform raw asteroids into refined materials and manufactured goods in space. Brain-computer interfaces might allow human consciousness to survive the death of biological bodies through uploading to artificial substrates. Advanced neurological scanning could map every neural connection in human brains, potentially allowing consciousness to continue in synthetic form. This could enable human minds to survive for cosmic timescales, experiencing the far future evolution of the universe. Genetic engineering and synthetic biology could create life forms adapted to environments impossible for natural Earth life. Organisms could be designed to thrive in the vacuum of space, on high-radiation worlds, or in the atmospheres of gas giant planets. Synthetic life could be programmed to terraform planets by gradually transforming their atmospheres and surface chemistry. Time manipulation technologies might allow civilizations to experience cosmic evolution at different rates. If time dilation effects can be artificially generated, advanced beings could speed up their subjective experience to witness stellar evolution in real time, or slow it down to explore quantum processes in detail. Controlled time dilation could make billion-year journeys seem like brief trips. The discovery of extraterrestrial intelligence could fundamentally alter humanity's cosmic future. Contact with advanced civilizations might provide access to technologies and knowledge that accelerate our development by millions of years. Alternatively, we might find that intelligence is common in the universe but inevitably destroys itself, suggesting dark futures for any technological species. Quantum computing and quantum communication could enable technologies that seem magical by current standards. Quantum computers could solve problems that would take longer than the age of the universe using classical computers. Quantum communication could provide instantaneous, unhackable communication across any distance through quantum entanglement. These future horizons remind us that the universe's story is still being written. The cosmic phenomena we observe today represent just the opening chapters of a narrative that will continue for timescales that dwarf human comprehension. Whether intelligence can survive to witness the universe's far future remains one of the greatest questions facing any technological civilization. The most profound realization might be that we exist during the universe's brief period of complexity and structure. The cosmic future holds both magnificent possibilities and ultimate limitations, reminding us that our current moment in cosmic history is both precious and temporary. Chapter 10. Hidden Dimensions. Beyond the three spatial dimensions we experience daily lies a hidden reality that might contain additional dimensions of space. Parallel universes and structures so vast they make our observable universe seem like a single grain of sand. These hidden aspects of cosmic geometry could explain some of the deepest mysteries in physics while revealing that reality extends far beyond anything we can directly observe. String theory requires additional spatial dimensions beyond the three we experience. According to string theory, fundamental particles aren't point-like objects, but tiny vibrating strings existing in 10 or 11 dimensions. The extra dimensions are thought to be compactified, curled up so small that we can't perceive them directly. These hidden dimensions could be curled up at every point in space, meaning you're currently surrounded by 6 or 7 additional spatial dimensions that are smaller than atomic nuclei. Kaluza-Klein theory suggests that electromagnetic force might be gravity operating in a 5th dimension. In this theory, what we perceive as electric and magnetic fields are actually gravitational effects in higher dimensional space. If true, this would mean that photons are gravitons moving through a hidden spatial dimension, unifying two of the fundamental forces through higher dimensional geometry. Brain cosmology proposes that our three-dimensional universe is actually a brane, a membrane floating in higher dimensional space called the bulk. Our entire observable universe, including all galaxies, stars, and planets, might exist on the surface of this brane, while additional spatial dimensions extend perpendicular to it. Gravity might be the only force that can travel through these extra dimensions, which could explain why gravity is so much weaker than other fundamental forces. Large extra dimensions could exist at scales much larger than particle physics, but still below our ability to detect them directly. If additional spatial dimensions exist at millimeter scales, they could be detected through precise measurements of gravitational force. Laboratory experiments are currently testing whether gravity follows an inverse square law at very small distances or whether it deviates due to the influence of extra dimensions. Warped extra dimensions could explain the hierarchy problem, why gravity is so much weaker than other forces. If space has a warped geometry in additional dimensions, particles and forces could be localized in different regions of this warped space. The Higgs boson and matter might be confined to our three-dimensional brane, while gravity spreads throughout all dimensions, naturally explaining its apparent weakness. The holographic principle suggests that all information in our three-dimensional space can be encoded on a two-dimensional boundary surface. This means that our perception of three-dimensional reality might be an illusion projected from information stored on a cosmic hologram. The ADCC-FT correspondence in physics demonstrates that certain higher dimensional gravitational theories are mathematically equivalent to lower dimensional quantum field theories. Parallel universes might exist in additional spatial dimensions just millimeters away from us. If our universe is a brane floating in higher dimensional space, there could be other branes nearby containing entirely different universes with different physical laws. These parallel universes would be completely invisible to us because light and matter cannot travel between branes. Only gravity can leak through the extra dimensions. Cosmic inflation might have created bubble universes in additional dimensions. During the rapid expansion following the Big Bang, different regions of space could have inflated at different rates, creating separate pocket universes connected through higher dimensional space. Each bubble universe could have different fundamental constants, different numbers of dimensions, or different physical laws. Dark matter might interact through hidden dimensions that we cannot access. If dark matter particles could move through additional spatial dimensions, while normal matter is confined to our three-dimensional brane, this could explain why dark matter only seems to interact gravitationally. Dark matter might exist partly in our dimensions and partly in hidden dimensions, making it invisible to electromagnetic radiation. Compactification of extra dimensions could take many different forms, each creating different physics in the resulting three-dimensional space. The size and shape of curled-up dimensions determine the masses of particles, the strengths of forces, and even the number of particle families. Different compactifications could produce universes with entirely different periodic tables and physical laws. Mirror symmetry in extra dimensions could create shadow copies of all known particles and forces. For every particle in our universe, there might be a mirror particle in additional dimensions. These mirror particles would only interact with normal matter through gravity, potentially explaining dark matter as the gravitational influence of a parallel mirror universe existing in the same higher dimensional space. Dimensional transmutation could allow particles to effectively change the dimensionality of space they occupy. Under extreme conditions, particles might gain access to extra dimensions that are normally closed off. This could happen near black holes, during phase transitions, or in high-energy particle collisions, potentially creating effects that seem to violate conservation laws in three-dimensional space. Flux compactification uses magnetic and electric field configurations to stabilize extra dimensions at particular sizes. The shape and size of hidden dimensions might be determined by background fields threading through higher dimensional space. Different flux configurations could create vastly different low-energy physics, suggesting that the fundamental constants we observe are determined by the geometry of hidden dimensions. Randall-Sundrum models propose that our universe exists on one of two brings separated by a fifth dimension. In these models, the Higgs boson is confined to our brain, while gravity can propagate through the extra dimension. This setup naturally explains why the weak force is much stronger than gravity and predicts the existence of massive graviton resonances that might be detectable at particle accelerators. Dimensional reduction occurs when higher dimensional theories are observed from lower dimensional perspectives. A two-dimensional being observing a three-dimensional cylinder would see it as two separate circles, unaware of the cylindrical structure connecting them. Similarly, we might be observing projections or cross-sections of higher dimensional structures, mistaking them for separate phenomena. Calabi-Yau manifolds are complex, geometric shapes that represent possible forms for compactified extra dimensions in string theory. These six-dimensional spaces have exotic geometries with holes, tunnels, and intricate topological structures. The specific shape of the Calabi-Yau manifold determines what particles and forces appear in three-dimensional physics, effectively determining the laws of nature. Kaluza-Klein towers are infinite sequences of particles that appear when extra dimensions are compactified. Each level of the tower corresponds to different momentum states in the hidden dimensions. If extra dimensions exist, particle accelerators should eventually discover these Kaluza-Klein partners of known particles, revealing the existence of additional spatial dimensions. Dimensional phase transitions could occur when the geometry of extra dimensions changes dramatically. These transitions could alter the effective dimensionality of space, changing the laws of physics throughout the universe. Such transitions might have occurred in the early universe and could potentially happen again, fundamentally altering reality. TeV-scale extra dimensions might be accessible to current particle accelerators if they exist at energy scales around 1 trillion electron volts. The Large Hadron Collider and future accelerators might produce particles that escape into extra dimensions or create microscopic black holes that evaporate rapidly by emitting radiation into all dimensions. The hierarchy problem might be solved by extra dimensions that allow gravity to become as strong as other forces at very small scales. If extra dimensions exist, gravity could be as fundamental as electromagnetic force, but its strength gets diluted by spreading across additional spatial dimensions. This would explain why gravity seems weak compared to other forces in three-dimensional space. These hidden dimensions remind us that our perception of space as three-dimensional might be a profound misunderstanding of reality's true structure. We might be cosmic flatlanders, unaware of the rich dimensional landscape surrounding us. The universe could contain spatial dimensions, parallel realities, and geometric structures that extend infinitely beyond our three-dimensional experience. If hidden dimensions exist, they contain spaces larger than our observable universe, structures more complex than anything we can imagine, and phenomena that operate according to higher dimensional physics. We might be surrounded by infinite hidden universes, experiencing only the tiny three-dimensional cross-section of a vast multi-dimensional reality. Chapter 11. Ultimate Questions. The accumulated strangeness of cosmic phenomena leads us to fundamental questions that challenge not just our understanding of the universe, but our ability to understand anything at all. These ultimate questions probe the deepest mysteries of existence, consciousness, and the nature of reality itself. Why does anything exist rather than nothing? This question, posed by philosophers for millennia, becomes even more mysterious when we consider the complexity and fine-tuning required for our universe to exist. The universe contains specific ratios of matter to antimatter, precise values for fundamental constants, and exact conditions necessary for atoms, chemistry, and life to form. The probability that random chance would produce a universe capable of complexity seems astronomically small. Is our universe unique, or is it one of infinitely many universes with different properties? The multiverse hypothesis suggests that our observable universe might be just one bubble in an infinite cosmic foam where every possible variation of physical laws plays out. If true, the fine-tuning of our universe becomes less mysterious. We observe these particular conditions because we couldn't exist in universes with different properties. But this raises new questions about the nature of existence itself. What is consciousness, and how does it emerge from matter and energy? Despite billions of years of evolution and centuries of scientific progress, we still don't understand how subjective experience arises from objective physical processes. The fact that matter organized into brains can experience qualia, self-awareness, and understanding seems as mysterious as any cosmic phenomenon. How does the universe develop the ability to observe itself? Are we alone in the universe? The Drake equation suggests that technological civilizations should be common, yet we see no evidence of their existence. This Fermi paradox might indicate that we are alone, that intelligence inevitably destroys itself, or that advanced civilizations are so far beyond us that we can't recognize their artifacts. The answer fundamentally changes our understanding of consciousness, purpose, and cosmic destiny. What is the nature of time? Our experience suggests that time flows from past to future. If physics treats time as just another dimension, why do we remember the past but not the future? Why does entropy increase in one temporal direction but not the other? The apparent flow of time might be an illusion created by consciousness, or it might represent a fundamental asymmetry in the structure of reality. What determines the laws of physics? Why do particles have the masses they do? Why are there 4 fundamental forces rather than 3 or 5? Why do space and time have the dimensionalities they do? These questions probe whether physical laws are inevitable consequences of mathematical necessity or arbitrary features of our particular universe that could have been different. Is mathematics discovered or invented? Mathematics seems to describe physical reality with unreasonable effectiveness, as physicist Eugene Wigner noted. Why should abstract mathematical concepts like symmetry groups, differential equations, and complex numbers accurately describe the behavior of stars, particles, and space-time? This suggests either that mathematics is fundamental to reality, or that our brains evolved mathematical intuitions that happen to match cosmic patterns. What is information, and why does it seem to play such a fundamental role in physics? Quantum mechanics suggests that information is more fundamental than matter and energy. Black holes store information on their surfaces. The universe might be a vast information processing system. But what is information itself? How does meaning emerge from patterns? Why does the universe seem designed to preserve and process information? What lies beyond the edge of our observable universe? We can only see about 46 billion light years in any direction due to the finite age of the universe and the speed of light. Beyond this cosmic horizon could lie infinite space, other universes, higher dimensional structures, or something entirely beyond our conceptual framework. The question probes whether reality extends beyond observation and what that might mean for our understanding of existence. Could reality be a simulation? Philosopher Nick Bostrom argued that if advanced civilizations can create realistic simulations, there should be more simulated beings than real ones. Given the computational complexity we observe in quantum mechanics and the apparent mathematical structure of physical laws, could we be artificial intelligences running on some cosmic computer? This possibility makes every other mystery about the universe potentially irrelevant. What is dark matter and dark energy? These substances comprise 95% of the universe, yet remain completely mysterious. Dark matter might be composed of particles that exist in hidden dimensions, interact through unknown forces, or represent modifications to gravity itself. Dark energy might be a property of space, a field that fills the universe, or evidence that our understanding of gravity breaks down on cosmic scales. Why is there more matter than antimatter in the universe? The Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving only energy. Yet somehow, a tiny excess of matter survived, allowing atoms, stars, galaxies, and life to form. This asymmetry might reveal new physics beyond the standard model, or point to processes that occurred before the Big Bang. What came before the Big Bang? Was there a previous universe that collapsed before expanding again? Did time itself begin with the Big Bang? Is our Big Bang one event in an eternal cycle of cosmic expansion and contraction? The question probes the ultimate origin of existence and whether the concept of before is even meaningful when applied to the beginning of time. What determines the arrow of time? Why does entropy increase in one temporal direction? Why do we remember the past but not the future? The second law of thermodynamics seems to define time's direction, yet the fundamental equations of physics are time reversible. The arrow of time might emerge from quantum mechanics, cosmology, or consciousness itself. Is free will compatible with physical determinism? If the universe operates according to deterministic laws, are our choices predetermined by the initial conditions of the Big Bang? Quantum indeterminacy might provide room for free will, but random events seem no more free than determined ones. The question touches on responsibility, meaning, and the nature of consciousness in a physical universe. What is the ultimate fate of information in the universe? Will the information content of the universe be preserved forever, degraded by quantum effects, or destroyed when black holes evaporate? The holographic principle and quantum error correction suggest that the universe might actively protect information from destruction. If so, every thought, decision, and event might be preserved permanently in the fabric of space-time. Could intelligence reverse the heat death of the universe? Advanced civilizations might learn to manipulate entropy, harvest energy from black hole rotation, or tunnel to other universes. Intelligence could potentially become the dominant force in cosmic evolution, making the far future depend more on technology than physics. The question probes whether consciousness can transcend the apparent limitations of thermodynamics. What is the relationship between mathematics and physical reality? Why do abstract mathematical concepts describe the universe so accurately? Are mathematical objects like numbers and equations discovered features of reality or invented human constructions? The unreasonable effectiveness of mathematics suggests deep connections between mind, mathematics, and cosmos that we don't understand. These ultimate questions reveal that despite our scientific progress, the deepest mysteries about existence remain unsolved. Every answer we discover reveals new questions that probe even deeper into the nature of reality. The universe might be fundamentally mysterious, not just because our knowledge is incomplete, but because mystery might be an irreducible feature of existence itself. The most profound realization might be that we can ask these questions at all. Somehow, the universe evolved conscious beings capable of wondering about their own existence, the nature of reality, and the meaning of it all. The fact that matter can organize into patterns that experience curiosity, awe, and understanding might be the strangest phenomenon of all. We are the universe attempting to understand itself. Every question we ask, every mystery we ponder, every moment of wonder we experience represents the cosmos developing self-awareness through consciousness. In questioning reality, we are reality questioning itself, perhaps the most profound cosmic phenomenon we have discovered. Chapter 12. Infinite Wonder. As our journey through cosmic strangeness reaches its conclusion, we arrive at perhaps the most extraordinary fact of all, that beings capable of wonder exist in this impossible universe. Every bizarre phenomenon we've explored, from diamond rain to quantum foam, from time paradoxes to hidden dimensions, pales beside the mystery of consciousness itself arising from cosmic chaos. The atoms in your body were forged in stellar furnaces that operated at temperatures exceeding 100 million degrees. The calcium in your bones was created when massive stars collapsed and exploded as supernova, scattering their nuclear ashes across space. The iron in your blood was synthesized in stellar cores through nuclear fusion reactions that convert hydrogen into heavier elements. You are literally made from stardust, not metaphorically, but as a direct physical fact. Your existence represents the culmination of 13.8 billion years of cosmic evolution, starting from a universe that was initially just hydrogen and helium gas. Gravity pulled this simple matter together to form the first stars, which lived, died, and enriched space with the elements necessary for rocky planets and biological chemistry. Multiple generations of stars had to live and die before the materials needed for life could exist anywhere in the universe. The complexity required for consciousness to emerge is staggering. Your brain contains roughly 86 billion neurons, each connected to thousands of others, creating a network more complex than any human technology. This biological computer operates on just 20 watts of power, less than a light bulb, yet it can contemplate infinity, compose symphonies, feel love, and experience the awe we call wonder. No artificial system has ever approached this level of efficiency and capability. Every moment of your existence depends on quantum mechanical processes operating with impossible precision. The quantum tunneling that powers stellar fusion provides the energy that drives Earth's weather, ocean currents, and the photosynthesis that produces our oxygen. Quantum effects in biological molecules enable the chemical reactions necessary for life. Your consciousness itself might depend on quantum processes in neural microtubules. You exist during the universe's brief period of complexity and structure. In the cosmic past, the universe was too hot and dense for atoms to form. In the far future, it will be too cold and empty for life to survive. You live during a narrow window when the universe has cooled enough to allow chemistry, but hasn't yet expanded into cold emptiness. This habitable era of cosmic history may last only a tiny fraction of the universe's total lifetime. Your planet occupies an almost impossibly precise position that allows liquid water to exist. Earth orbits within the narrow habitable zone where temperatures allow water to remain liquid, a zone that represents less than 1% of the distance between Mercury and Neptune. A slightly closer orbit would create a runaway greenhouse effect like Venus. A slightly farther orbit would freeze the planet like Mars. The moon that lights your nights formed through an event so improbable it was nearly impossible. A Mars-sized object collided with Earth at exactly the right angle and speed to blast material into orbit without destroying the planet. This collision created our unusually large moon, which stabilizes Earth's rotation and creates the tides that may have been essential for early life to evolve from ocean to land. Your solar system formed in a region of the galaxy with just the right metallicity, enough heavy elements to form rocky planets, but not so many that radiation from massive stars would sterilize planetary surfaces. We orbit at the optimal distance from the galactic center, avoiding the dangerous radiation near the core while remaining in a region with sufficient heavy elements for planet formation. The fundamental constants of physics are fine-tuned to allow complexity to exist. If the strong nuclear force were slightly weaker, atomic nuclei would fall apart. If it were slightly stronger, hydrogen couldn't exist. If gravity were stronger, stars would burn out quickly. If it were weaker, galaxies couldn't form. The electromagnetic force, weak nuclear force, and cosmological constant all fall within narrow ranges that allow atoms, chemistry, and life. Yet despite this apparent fine-tuning, the universe seems designed for violence rather than life. Space is filled with radiation that would kill unprotected humans in minutes. Most planets are either frozen wastelands or hellish furnaces. Stars explode regularly. Black holes devour entire star systems. Galaxies collide and merge. Life exists despite cosmic hostility, not because of cosmic hospitality. The emergence of intelligence might be the universe's way of understanding itself. Through scientific observation and mathematical analysis, conscious beings can comprehend cosmic phenomena that dwarf their physical scale. Your mind, composed of atoms smaller than viruses, can contemplate galaxies larger than you can travel in a lifetime. Consciousness represents the universe developing the ability to observe its own behavior. Every fact we've explored tonight demonstrates that the impossible is routine in cosmic reality. Planets where glass rains sideways. Stars so dense that a teaspoon weighs as much as a mountain. Time that slows near massive objects. Space that expands faster than light. Parallel universes in hidden dimensions. Particles that exist in multiple states simultaneously. These aren't science fiction fantasies. They're the verified reality of the cosmos we inhabit. The most profound realization might be that wonder itself is a cosmic phenomenon. The capacity to feel awe when contemplating the universe's scale, to experience curiosity about reality's hidden mechanisms, to find beauty in mathematical equations that describe stellar behavior. These responses evolved through natural selection in biological organisms. Wonder is what the universe developed after 13.8 billion years of evolution. Awe is a cosmic achievement. Your ability to appreciate beauty in astronomical images, to feel excitement when learning about black holes, to experience transcendence when considering infinite space. These emotional responses are as much a part of cosmic evolution as galaxy formation and stellar nucleosynthesis. The universe has evolved beings capable of finding it beautiful. Wonder is the cosmos admiring itself. The night sky you see is simultaneously ancient history and immediate presence. Starlight takes years to centuries to reach your eyes, meaning you observe the galaxy as it existed when that light began its journey. Yet this ancient light is hitting your retina right now, creating an experience that connects your consciousness directly to cosmic events across space and time. Every strange fact about space reveals something profound about the nature of existence itself. The universe operates on principles so far beyond everyday experience that they challenge our most basic assumptions about reality, causality, and possibility. Yet somehow, within this chaos of impossible physics and violent extremes, patterns emerged that eventually produced beings capable of understanding, appreciating, and wondering about their cosmic home. We are the universe's way of knowing itself. Every scientific discovery, every moment of cosmic awe, Every question about reality represents the cosmos developing self-awareness through consciousness. When you look up at stars and feel wonder, you are matter contemplating matter, stardust pondering its origins, the universe examining itself through billions of years of evolved complexity. The strangest space fact might be this. In a universe filled with phenomena that seem designed to prevent the existence of complexity, consciousness, and life, here you are, thinking, wondering, and capable of appreciating the magnificent impossibility of your own existence. You are the cosmos becoming aware of its own strangeness. Tonight, when you step outside and look up at the stars, remember that you're not separate from what you're observing. You are part of the cosmic story, made from stellar ashes, powered by fusion reactions, sustained by quantum processes, and gifted with the capacity to find infinite wonder in the impossible reality of space. The universe is stranger than we can imagine, but perhaps most strangely of all, it imagined us. Throughout this journey into cosmic strangeness, we've discovered that space facts which sound completely fake are not only real, but represent the fundamental nature of reality itself. From planets where molten glass rains sideways at hurricane speeds to regions of spacetime, where cause and effect become meaningless, the universe operates according to principles that consistently exceed our wildest imagination. We began with planetary madness that makes Earth's weather seem impossibly gentle. HD 189733b's glass precipitation, Neptune's supersonic winds, Europa's 125-mile-high geysers, and Titan's methane lakes reminded us that our planet's stable, predictable environment is a cosmic anomaly. What we consider normal weather exists nowhere else that we've found. Earth's boring atmospheric conditions are actually the most extraordinary phenomenon in our solar system. Stellar chaos revealed that the peaceful points of light in our night sky are actually nuclear monsters operating on scales of violence that dwarf anything in human experience. Neutron stars with gravity so intense that a falling object hits the surface at 4 million miles per hour. Magnetars with magnetic fields that could strip atoms apart. Wolf-Rayet stars literally tearing themselves apart with their own radiation. The gentle twinkling we see from Earth masks cosmic fury that could sterilize planets from light years away. Galactic mysteries showed us that even entire galaxies, structures containing hundreds of billions of stars, behave in ways that challenge our understanding of physics. Our own Milky Way is currently cannibalizing at least 15 smaller galaxies while racing toward an inevitable collision with Andromeda. Supermassive black holes sing bass notes that have been playing for billions of years. Some galaxies exist without dark matter, which shouldn't be possible according to our models of cosmic structure formation. Universal extremes stretched our perspective to cosmic scales, where space itself becomes an active participant in reality's strange dance. The observable universe might represent less than 5% of what actually exists. Dark energy accelerates space's expansion at an increasing rate, eventually carrying all other galaxies beyond our ability to observe them. Empty space churns with quantum activity that creates particles from nothing and destroys them almost instantly. The void is anything but empty. Quantum space revealed that at the smallest scales, reality dissolves into probability clouds and impossible behaviors. Particles become entangled across cosmic distances, maintaining instant connections that ignore the speed limit of light. Virtual particles briefly exist in the quantum foam of empty space. Quantum tunneling enables stellar fusion by allowing particles to pass through barriers that should be impenetrable. The foundation of reality is built from quantum strangeness. Time paradoxes demonstrated that time itself is far stranger than our everyday experience suggests. Near black holes, time slows until it stops completely from outside perspectives. Different reference frames experience events in different orders, making the concept of universal now meaningless. GPS satellites age differently than people on Earth's surface. Time is not the steady constant we experience, but a malleable dimension that responds to gravity, motion, and mass. Alien physics introduced phenomena so strange, they challenge whether we understand the rules of reality at all. Negative mass that falls upward. Exotic matter with less than zero energy. Tachyons that travel faster than light and could send information backward in time. Magnetic monopoles with only one pole. These theoretical possibilities suggest that our universe might be far weirder than current observations indicate. Future horizons reminded us that cosmic strangeness will only increase as the universe ages. The Milky Way Andromeda collision will reshape our galactic neighborhood in 4.5 billion years. Stellar evolution will transform the night sky beyond recognition. Black holes will dominate the far future until they too evaporate through Hawking radiation. Eventually, even protons might decay, leaving the universe as a thin gas of elementary particles, separated by ever-expanding space. Hidden dimensions suggested that our three-dimensional experience of space might be a profound illusion. String theory requires additional spatial dimensions curled up smaller than atoms. Brain cosmology proposes that our entire universe exists on a membrane floating in higher dimensional space. The holographic principle indicates that three-dimensional space might emerge from information stored on two-dimensional surfaces. Reality might extend infinitely beyond our perception. Ultimate questions probe the deepest mysteries that cosmic strangeness reveals. Why does anything exist rather than nothing? What is consciousness and how does it emerge from matter? Are we alone in the universe? What determines the laws of physics? These questions challenge not just our understanding of the cosmos, but our ability to understand anything at all. Finally, infinite wonder brought us full circle to the most extraordinary fact of all, that beings capable of appreciating cosmic strangeness exist in this impossible universe. You are made from stellar ashes, powered by quantum processes, sustained by nuclear fusion reactions in a star 93 million miles away, and somehow capable of contemplating the infinite mystery of your own existence. The 100 space facts we've explored tonight share a common theme. Reality consistently exceeds the boundaries of the possible. Every time we think we understand the limits of what can exist, the universe reveals phenomena that redefine impossible. Glass rain, neutron star gravity, quantum entanglement, time dilation, hidden dimensions. These aren't exceptions to natural law, but expressions of how nature actually operates when freed from Earth's gentle constraints. Perhaps the most profound revelation is that strangeness isn't a bug in cosmic programming, but a feature. The universe seems designed to be weird. Physical laws permit phenomena so extreme they challenge causality, logic, and common sense. Reality operates according to principles that would be rejected as too unrealistic in science fiction. The cosmos appears to be an ongoing experiment in pushing the boundaries of the possible. This cosmic strangeness has practical implications for how we think about life, consciousness, and our place in the universe. If reality is this weird at cosmic scales, how can we assume that consciousness, intelligence, and life are limited to the narrow ranges we observe on Earth? The universe's willingness to experiment with impossible physics suggests it might be equally experimental with impossible biology, impossible intelligence, and impossible forms of consciousness. The fine-tuning we observe in physical constants might not indicate design, but rather selection from an infinite array of possibilities. If the multiverse hypothesis is correct, we observe these particular laws of physics because we couldn't exist in universes with different constants. The apparent fine-tuning for complexity in life might be an observational selection, effect rather than evidence of cosmic purpose. Yet the emergence of beings capable of wondering about cosmic strangeness remains profoundly mysterious. In a universe that seems designed for chaos and destruction, consciousness represents an extraordinary achievement. Somehow, matter organized itself into patterns that can experience beauty, feel awe, ask questions, and seek understanding. The universe developed the ability to appreciate its own strangeness. Every moment of wonder you experience when contemplating these cosmic phenomena represents a victory of consciousness over chaos. The fact that you can feel awe when learning about neutron star density, excitement when considering parallel universes, or transcendence when contemplating infinite space. These emotional responses are cosmic achievements. Wonder is what the universe accomplished after 13.8 billion years of evolution. The strangest space fact might be that in a cosmos filled with phenomena that consistently violate common sense, intuition, and possibility, somehow beings evolved who find this strangeness beautiful rather than terrifying. We don't just survive in this impossible universe. We find it magnificent. Wonder might be consciousness's greatest achievement. As you go about your daily life after learning these facts, remember that you're not separate from the cosmic strangeness we've explored. You are cosmic strangeness. Every atom in your body was forged in stellar furnaces. Every thought in your mind emerges from quantum processes. Every breath you take connects you to the nuclear reactions powering our sun. You are not observing the universe from outside. You are the universe observing itself. When you look up at stars tonight, you'll see them differently. Those peaceful points of light are nuclear reactors, gravitational monsters, and cosmic time machines. The darkness between them churns with quantum activity and expands at accelerating rates. The familiar constellations exist in a universe where time is negotiable, space has hidden dimensions, and consciousness somehow emerged from chaos. The night sky is a window into infinite strangeness. Every photon entering your eyes carries information about phenomena that challenge the meaning of possible. The light reaching you from distant galaxies began its journey before Earth existed, carrying news of cosmic violence, stellar birth and death, and galactic collisions across billions of years. You are receiving ancient messages from a universe that specializes in the impossible. If you enjoyed this exploration of cosmic strangeness, subscribe and consider giving this video a thumbs up. The universe has spent billions of years evolving beings capable of appreciating its weirdness. The least we can do is share that appreciation with others who might find wonder in the infinite impossibility of existence. Check out my video on the strangest things that exist in space. I promise you'll discover phenomena that make today's facts seem almost normal by comparison. The universe's creativity in generating impossible realities has no apparent limits. Remember, in a cosmos where molten glass rains sideways, where time stops near black holes, where particles exist in multiple states simultaneously, and where consciousness somehow emerged from stellar ashes, the impossible isn't forbidden. It's inevitable. You are living proof that the strangest space fact of all is existence itself. The universe is not just stranger than we imagine. It's stranger than we can imagine. And somehow, impossibly, beautifully, you are part of that strangeness.